Okay, we're looking at volumes of revolution. So there's some diagrams there. These are graphs of some different types of functions. So we want to think about what would happen if we rotated these one revolution about the x-axis. So what shape, three-dimensional shape, would occur? So if you take the first one, that's just a linear function between two variables. If we rotate that around, then we would end up getting a cone. The next one is not really a normal shape that we would talk about. It's just basically, we call it a special cone. Okay, it would still have a circular base. It still has an apex, but the side is not straight. Special cone. Next one, obviously, would be a sphere. Is basically part of a cone. Kind of cuts off before that linear function reaches the x-axis. So it's part of a cone, which has a special name in math called a frustum. Okay, next one, if you rotate that, that's actually what we call a bell, right? So the shape of an old-fashioned bell. Okay, so that looks like kind of like a cubic that's rotated. And then this, when you rotate, is really just going to be a cylinder. So that last one is really important when we're considering how to calculate the volume of any function. It goes back to the area under a curve and approximating with an infinite number of rectangles that are formed. So just to summarize here, the shapes that you imagined are called volumes of revolution, and it is possible to determine the actual volume of the shape if the functions that bound the area is known. Let's look more closely at the area in the middle of the bottom row. A narrow rectangle, the ith rectangle, that is bounded by the x-axis is drawn and shaded. So now if we take that particular one, if that happened to be exactly flat at the top, it would be a perfect cylinder. It's not flat right now, but if we get our change in x, this is really delta x, small enough, then it is. So the height of the rectangle, so if our function is called f of x, then it would be f of x I, where it tells you which rectangle you're dealing with, that particular x value, and the width of it, as I said, is delta x. So imagine rotating the rectangle around the x-axis one complete revolution. The shape that would be produced is a cylinder, as long as that, as I said, delta x is small. Sometimes we call that a disk when we're considering areas and volumes. Well, actually, in this case, volumes. So the volume of that cylinder, so back to basically math 9 and 10, remember the volume of a cylinder is pi r squared, the area of the base, times the height of the cylinder. Okay, and so in this case, so it would be pi, but what's our radius? Okay, so our radius is our radius of the cylinder is really the height of the rectangle, so it's going to be pi times f of xi squared, and then the actual height of the cylinder, so think of it on its side, is the width of the rectangle, delta x. So now by imagining infinitely many adjacent disks of infinitely narrow height, creating the volume of the shape produced by rotating the area under F, if we add up the volume of all of those disks, then we get the volume of revolution. So think about your summation notation. We're adding up all of those disks. So pi, again, f of xi squared dx. And so I is going to go from 1, x1, then x2, then x3, all the way to infinity, right? An infinite number of disks in there. And so that leads to integral notation. So from a to b, so those are your boundary points, boundary x values, pi f of x squared dx. Okay, so that's the integral, remember, is basically when n goes to infinity, it equals the integral here. Oftentimes we show the pi out front for this. Okay, so let's practice one. Determine the volume of the solid produced by revolving the area between y equals 2x and the x-axis, 1 revolution about the x-axis from 0 to 6. You might want to do a little sketch. Okay, so y equals 2x. Just give me a sec here. I'm going to change the color. So something like that. And we want to go from 0 for x, so from here, and let's say 6 for x is here. All right, and let's just do this. So vertical line from there. Okay, so we want to take this and rotate it, so it's going to be a cone. Obviously, you could actually use just the area of the cone, volume of a cone formula, but we're going to use integration here. All right, so volume will equal pi times our function, that's 2x squared dx, going from x equals 0 to x equals 6. Okay, so let's just simplify that a little bit. It's 4x squared dx. So you might want to bring the 4 out. Okay, and then integrate, that's going to be x cubed over 3 from 0 to 6. Okay, I'm going to substitute in. So that's going to be 4 pi over 3 times 6 cubed minus, really, 4 pi over 3 times 0 cubed, which is 0. And then just simplify it. Don't use the decimal form of pi. So if you go 4 times 6 cubed divided by 3, you get 288 pi, and that would be units cubed. Okay. Now, if you were to calculate the volume of a cone, so remember, before you knew calculus, it would be pi r squared times the height divided by 3. In this case, r here is going to be at 6. The radius will be 12, because the function is 2x. So when x is 6, y is 12. So the radius would be 12 squared. The height would be 6 units divided by 3. Okay, so that's going to be 144 times 2 is 288 pi. Okay, so this one you can actually, when it's a three-dimensional shape that you already know the formula, it's actually easier to do it that way, but they're not always going to be a cone or a cylinder or a prism or a sphere. Okay. Case in point, the next one. So, determine the volume of the solid produced by revolving the area under y equals sine x, 1 revolution about the x-axis from pi over 2 to 5 pi over 6. So, there's that. We go like this. And we used blue, let's go red. So, there's your sine function. And we want to go from pi over, so that's pi, here's pi over 2, to 5 pi over 6 is just short of pi. So it's going to be in here. This goes up here, so we won't, and this is 5 pi over 6. All right, so you can clearly see that it's a positive function. So, and you're rotating that, the volume equals pi, so from pi over 2 to 5 pi over 6, and that's sine, well, we're squaring it, so we might as well do sine squared x dx. Okay, now, how do you integrate that? So we have to think back to our trig substitution. In this case, I would when it's just sine squared or cos squared, use your identities. So take a look at your formula sheet. Okay, and look for, obviously, sine squared. Sine squared is, you can see it at a couple places. Sine squared plus cos squared equals 1. So replacing that with 1 minus cos squared is not really going to help you. You still have an even exponent on a primary trig function. Take a look at your cos of 2x, because in there, there's some sine squareds. So we want to try, if we can, getting this into something that's not squared. So you'll notice that cos of 2x equals 1 minus 2 sine squared x. Okay, so there's a sine squared in our integral, and we want to get it down to something that's not squared. So this would be the way. So now if I bring the 2 sine squared to the right, and the cos of 2x to the left, and divide by 2, I'm just going to show it out front. Okay, and that's just a common method that we can use to help us, using that cos of 2x identity. So your brain may be a little rusty from the spring, but this will help unrustify it. So this is going to be pi over 2, 5 pi over 6. So now it's 1/2, which I can actually show the half out front. So it's going to be pi over 2 times 1 minus cos of 2x dx. So we haven't done any substitutions. We've just used an identity to replace sine squared x. So now, when we integrate this, I'll use brackets, so that's just going to be integral of 1 is x. And then if you want to use a substitution just to make sure, but anytime the argument has a coefficient of 2, it's going to be 1/2 the integral of cos. But if you're not sure, again, you don't want to just randomly put it in, not being sure about it. So that's really going to be minus, okay, and then cos of u. Well, the integral of cos of u, so remember sine, derivative of sine is cos, derivative of cos is negative sine, so now this is going to be positive sine. So this is going to stay subtracting, and then it's going to be 1/2 sine of 2x, and this is from pi over 2 to 5 pi over 6. All right, so now, so here pi over 2, so we'll have 5 pi over 6 minus 1/2 sine of 2 times 5 pi over 6 minus pi over 2 times pi over 2 minus 1/2 sine of 2 times pi over 2. Okay. So now 5 pi over 6 minus 1/2 sine of 5 pi over 3. You could expand out the brackets. I'm just going to finish in here. So sine of 5 pi over 3. So that's going to be negative root 3 over 2. Okay. And sine of sine of pi is 0. So we just leave it as pi over 2. And then simplify. Okay, you can do this all kind of in more steps, or less steps, I should say. So that's going to be pi squared over 4, and this is going to be 5 pi squared over 12 plus root 3 over 4 pi minus pi squared over 4. So I can simplify the pi squareds. And that's going to be common denominator. So 5 pi squared minus denominator of 12 minus 3 pi squared over 12, which is 2 pi squared over 12, which is pi squared over 6. And again, it's units cubed. Okay. You could factor out the pi if you wanted. There'd still be a pi in one of the terms, so I would just leave it like that. All right. Next one is underneath. It says, determine the volume of the solid produced by revolving the area enclosed by those two functions. The x-axis, around the x-axis, 1 revolution. Okay, so it's kind of nice to think about what it's going to look like. Okay. This doesn't give you those boundary values, so we actually have to see where they intersect. So I'll use red. So 4 root x, so it's going to be something like that. And y equals 2x, so that's going to be, I'll use a line here. Maybe I'm going to make it a little, rotate it so it's just a little bit easier to see. So I don't have a scale on my graph, right? But I want to, so I already know that they intersect at 0, 0, just from the knowledge of those two functions, but not sure where they intersect. This is what we're going to rotate. Okay, so we want to find the point of intersection to start. So think about here, we want to find where 4 root x equals 2x. Okay, so I divide by 2 root x equals x. I'd square both sides. So that would be 4x equals x squared. And then x squared minus 4x. Don't divide by x, because then you only get one point of intersection, which doesn't make sense. So then this is x times x minus 4. So x equals 0 and 4. So there's your 0. And then at 4 here, your y value is 8. Okay? So do you really need to know the y value? Actually, you don't. So you just want to rotate between 0 and 4. Biggest mistake people make here is they subtract the functions and then they rotate it. Okay? Sometimes that will work, but in this case, no. If the functions were both linear or something like that, then that would be fine, but this isn't. So think about it as you're taking, in this case, this radical function, you're rotating it, so you're really getting this volume here, and then you're taking your line and you're rotating, oh, I guess it would mean there, right? So you're finding the volume to here, and then you're rotating the line here, and when you rotate that, it's going to be like this. So you're subtracting that. I always think about it as making a donut. It's a big blob of dough. Then they take out the donut hole. Now they call those Timbits at Tim Hortons. But you have to have the volume first before you take that out. So you're subtracting the volumes. So that means here the volume will be the larger function, so 4 root x, the volume of that rotated. and that's from 0 to 4. And then subtract the volume of the inside function, again 0 to 4, and that's going to be 2x. Okay. You can factor out the pi, you can show it as one integral. So when you do, because it's got the same indices, that's going to be 16x minus 4x squared dx, which is a pretty straightforward integral to take. So that's going to be pi times 16x squared over 2 minus 4x cubed over 3 from 0 to 4. And so that's really 8x squared. So in here, we're going to have 8 times 4 squared minus 4 times 4 cubed over 3. Just going to erase this. Minus pi times, and basically that's going to be 0 minus 0, right? So the whole thing goes to 0. And so what's this? So 8 times 16 is 128, minus 4 to the 4th is 256 over 3. Okay, then common denominator would be 384 minus 256 over 3, which ends up being 128 over 3 pi. We end up showing pi at the end, and again, units cubed. So that one we just had to make sure we found the points of intersection because it didn't specify. Okay. And the last one, which is at the top right, determine the volume of the solid produced by revolving the area enclosed by y equals 2 to the x, the x-axis, and y equals root of x minus 1. One revolution about the x-axis from 0 to 2. Okay, so again, let's take a look. Okay, so I'll use blue. And y equals 2 to the x. So we know it has a y-intercept of 1 there. Something like that. Root of x minus 1. It's got an x-intercept here. And something like that. Okay. And the reason why it says with the x-axis as well, because we're going from 0 to 2. So if we're starting at 0, the next function isn't there, right? So we're really going, so this is 1, 2 would be here. So we're taking this and rotating it, okay? So really think about if we just had y equals 2 to the x from 0 to 2, we would rotate that, okay? Then what are we subtracting? We're subtracting the other function, root of x minus 1, just from 1 to 2. So now our indices are going to be different. Okay, so our volume here is going to be pi times, so the larger function from 0 to 2 of 2x squared dx. And we're subtracting pi times from 1 to 2 of root x minus 1 squared dx. Okay, so that's going to be pi 0 to 2 of 2 to the 2x. And then when you square a square root, you just get x minus 1. So that's going to be easy. Take a look at, if you can't remember, take a look at your formula sheet. So if you are integrating, so remember derivative of, say, b to the x equals b to the x ln b. Okay, so if you solve this for b, you've got a factor of ln b, right? And if you're integrating, so from that, and again, you might want to substitute u for 2x. You're just going to have a factor of 1/2 out if you remember that. So totally up to you. So you could go, okay, u equals 2x, du equals 2 dx, so a half du equals dx. So this is going to be pi over 2. And then it's going to be, so if we solve this, it's going to be 2 to the 2x over ln 2. Okay, from 0 to 2. And this is going to be x squared over 2 minus x from 1 to 2. So then we're going to substitute. So pi over 2, 2 to the 2 times 2 over ln of 2, lots of 2's, minus, actually you can keep the bracket there, minus 2 to the 2 times 0 over ln of 2, and minus pi times 2 squared over 2 minus 2. That. Minus 1 squared over 2 minus 1. All right, so then we have pi over 2. This is going to be 2 to the 4th, same denominator, minus 2 to the 0, right? So that's going to be, actually, I'm going to evaluate that in, sorry. Okay, so this is going to be 2 to the 4th, which is 16 over ln 2, and then common denominator, then 2 to the 0 is 1, so minus 1. And here, 4 divided by 2 is 2, minus 2 is 0, minus 1 half minus 1 is negative 1 half, so that's going to be positive 1 half. So that's going to be 15 pi over 2 ln 2 minus pi over 2. Okay, you could show this in different ways. You could factor out a pi. You could actually pi over 2 you could factor out. And then you'd have 15 over ln 2 minus 1. You could find a common denominator. So that would be 15 pi minus ln 2 pi over 2 ln 2. You could show this as ln 4. 2 squared is 4. Yeah, you could factor out the pi. So many ways of showing that. And this is units cubed. Okay, so there's a bunch of examples for calculating volume.